And welcome everybody today. I'm glad everybody could attend. Today we'll be talking about installing or introducing sustainable or more efficient systems, mechanical systems into historic structures. So to start with, it's always good to understand what you're likely to find in a historic structure. And so we'll start with steam boilers. Hang on one sec. The steam boiler, as advertised, produces, turns water into steam, and then that steam is distributed around the house to typically radiators or other type of heat exchange equipment. You have a single pipe radiators, which, as the name implies, I have a radiator here in the center with a single pipe connecting it, and then I have usually an automatic air vent on the side. And the way that works is the steam comes into the radiator, it displaces the air out that vent, and when that vent senses the steam, it shuts off, and so then the radiator heats up and condenses water. The water that comes out of that steam then has to go back out that same pipe. So one of the things you want to be sure not to do on these is throttle this valve, or else you can cause water to back up, or you cause steam knocking and things like that. And the other type of steam system you're likely to find in a historic house is a two-pipe radiator, and in that case you have steam entering in through a valve, either at the top or bottom, and then on the other side you have a pipe leaving with a small thermostatic trap, and that trap does the same thing as that air vent. It's comparing condensate, looking for condensate or steam, so when it senses steam, it shuts off so that steam stays in the radiator and doesn't go down back to the boiler until it's ready. And then you have hot water boilers that produce hot water that's usually circulated around with a pump. These days, it's usually circulated. Back 100 plus years ago, it was common, or fairly common, to have a gravity system, which used the buoyancy effect of hot water. So there was no circulator. It was a very quiet, very expensive system because you had huge piping that you had to install because there was no motivating force other than the temperature difference to drive the moisture or the water around. Those radiators, of course, are two-pipe radiators. Always, I have a supply pipe in and a return pipe out. Usually, there's an air vent, a manual air vent that you have to vent the air out of at the start of the season, and sometimes periodically as air can build up in the radiators and keep the radiator from heating up. And then another type of radiator is a pipe radiator that can be wrapped on the wall or ceiling. It can be built into furniture or built-ins in the house, and you'll see these around Oak Park fairly often. And there's just so many different styles of radiators out there. I was in a building the other day where there's probably 30 radiators and probably 15 different styles, and so that's not uncommon at all to have a lot of styles of radiators. If you want to add some thermal control to those radiators, if you're having trouble with overheating in spaces, one of the things you can do is add a thermal control valve. Danfoss is one of the manufacturers, and it basically replaces. It's a little thermostatic head, non-electric. It's just all mechanical. This connects on the two-pipe radiators, connects to the control valve. You replace the control valve with this, and then this, you just dial it hot or colder. You can get it with remote sensors if it's an enclosed radiator, and then if it's a single pipe radiator, you can still control, but you take that automatic air vent off the side, and you install this part of the valve controller. And then you put that vent valve back onto the side of this controller. And now, instead of controlling the steam coming in, I'm controlling it by slowing down the air leaving the radiator or stopping it from leaving the radiator. So you can actually, this radiator will shut off if the space is satisfied. And the way you do this is you put a thermostat for the system in the place that takes the longest to heat. And then you put these type of valves on your radiators in any space that's overheating, and then it'll keep it more comfortable and save energy and make it more efficient. Lastly, if you, a lot of houses will have a forced air system. Of course, a 100-year-old house would have been heating only. It's these big behemoth heaters that were terrible efficiency. This is a little more modern radiator. You see the flue going out to a chimney. It also has a cooling coil that's installed in the supply duct, and that would be connected to a remote condensing unit like one of these. So that's a typical air system that you might find in a house in our area. Looking at some of the sustainable options that we have. I'm going to focus today, just for time, on ground source heat pump systems and air source heat pump systems. This covers the bulk of the higher efficiency options. So on the ground source side, you got a self-contained or a package system, which is just one box inside that does everything. You can do a split system, and the rest of these items are all kind of the same for both air source and ground source. You can get a split system that one box outside or one box inside connected to the ground loop connects to an air handler or something. I'll go into these in a little bit more detail. You got a water source variable refrigerant flow or VRF system. You got a water to water system, standard temperature 120 and high temperature of 160. And then with the air source, it's all basically the same equipment, only just with an outside box interacting with the air environment instead of the ground environment. So generalities here, just kind of the reasons why we might consider looking at geo is they are typically more efficient than all other available residential systems. They have lower CO2 emissions, so they're good at reducing that footprint, lower operating costs, lower site utility use. And in a traditional system, you might have a gas furnace and an electric air conditioning unit. These are all electric systems, so you're going to get rid of your gas service or gas load and have an all electric winter and summer. You've got lower maintenance costs because you have no outside equipment. You have a longer average equipment life of maybe 5 to 10 years typical over air source equipment, and then they work at full rated capacity year round, which is kind of a big deal. As heat pumps, as the temperature changes, and this is true of all heat pumps, as it gets colder, you have reduced capacity, but because we can design our well field, we can actually control how low that temperature goes, and so we can get full capacity year round. The caveat here is it's going to be significantly more expensive to install, because you got to install the loop field. So looking at so how the system works is the ground has a stable earth temperature. Here in the Chicago area, we're about 52 degrees when the deep earth average temperature, and about almost 50% of the sun's energy is absorbed by the ground, which helps in that process of keeping the ground at a stable temperature, which is a great place to, where this environment, the air environment, is changing from maybe negative 10, 0 in the wintertime up to 80s and 90s in the summertime. The ground starts at 52 and then just moves one way or the other as we put energy in or take energy out. Some people think, we'll say geo has free energy. Well, it does, but you got to spend some energy to capture that energy. So geo system has a coefficient of performance of about 4 to 5, depending on the equipment you buy. That means for every unit of energy I put to run the fan, the compressor, the pumps, I get 3 to 4 units of energy out of the ground that's delivered to the house. Those two are added together to deliver to the house. Air source heat pumps are the same thing. It's just this bottom component is derived from the air, and it's not as much. They're not quite as efficient. They're maybe 2 to 3 versus 3 to 4 on that. So why do we care? We have the heating, air conditioning in a typical single family house comes in at about 73% of the total energy consumption. When you add the geothermal component, I take almost 50% of the total and provide it from the earth, and now I'm only using 24% of electric energy to help me do the same load. So you're basically cutting you're cutting in half the amount of energy consumed on site in a typical residence. Looking at how the loop field is installed, this is the most expensive piece. In our Chicago area, vertical drilling is the typical, and there's other methods that could be talked about at other times, but this is the typical method. And some of the drill rigs are really big, big, huge, trucks. This particular style is on tracks, and it's fairly narrow. It'll fit down an 8-foot gangway or through a 6-foot fence section, typically, pretty comfortably. It has a little bit of a head height issue. This thing folds back, but it's still maybe 10 or 12 feet tall that it has to get through. So, like, it would not fit through this. This is at Glessner House, where this was just about a week and a half ago. We were drilling wells in the courtyard there. This is a Frank Lloyd Wright house here in Oak Park, where we drilled last summer to put a loop field in the front yard. But if you can get this rig in, and you got to be careful of trees, not just the root system, not to compress it or cut through it too much, but also the overhead canopy. You can't lift this thing up if you can't get through the trees. But if you can get the rig in, usually you can drill a hole. Looking at the loops themselves, these come from the manufacturer. They're to the length that you're going to go. In the area I typically am drilling somewhere between 150 to 500 feet deep on the boreholes. When you have a small lot, you need a certain amount of pipe in the ground to handle the loads that you're going to see moving between the ground and the house. and you can either go less boreholes, deeper, or more boreholes, shallower. It kind of depends on what your driller likes to do and how much ground you've got and, available to put it in. But so these come pre-made. This is what the end looks like. This is how we can get 2 pipes down a 500-foot deep hole. These come in 3/4, 1.25 inch diameter, and then there's this factory manufactured things put on the bottom that causes a real sharp turn and good flow. And then this is filled with water and weighted down and inserted in the drilled hole. And it looks like that when it goes into this ungrouted hole. And then we come in and we fill it from the bottom up with a thermally enhanced grout, which is just bentonite clay mixed with sand and sometimes carbon and other things to improve the thermal conductivity of the grout. Because the whole goal here is to move energy in from this pipe into the ground and from the ground into the pipe. And so you need a good conductive material. The other piece the grout does is it's required by the state well drilling code to ensure the aquifer that we might drill through doesn't get contaminated with surface water or aquifers transferring between themselves or whatever. So it's just a protective environmental. And then once we've drilled that hole, we come back in and we sometimes we'll connect the pipes together outside. We do that at about 4 to 5 feet below the ground, and then trench them over or directionally bore them into the building. Sometimes we'll bring them in individually. A 500-foot hole I typically will bring in individually. So I'll have a bunch of these lined up depending on how many holes you've got. For the shorter holes, sometimes we'll gang them together, maybe 3 or 4 shorter bore holes gang together to a single set of pipes in the house. And then this type of system gets cleaned up and headers made, and then the piping is directed to all the geo equipment in the house. This is one of the package units or self-contained units. This is an upflow unit. Air comes in the side here and then goes out the top. This comes in a downflow unit. So you might have a situation where you have a crawl space with ductwork and you need something to blow down into it. So we can get this in that configuration. We can also get it into a horizontal version. You can replace a direct replacement for a furnace system. You can put in a new installation. And like most of these heat pumps, it has the ability to generate domestic hot water, which happens in the summertime. It's almost free because it's essentially taking water that would have been discarded to the ground or rejected to the ground and rejects it to a tank. Here's a setup that shows that. So I've got an upflow heat pump. Here's the pump that circulates to the ground loop. And then this tank is preheated by air. So anytime this unit is running and heating or cooling, it's putting hot water into this tank if the tank's below set point. And then as water is drawn into the house, it flows out of this tank into the traditional. This is an electric hot water tank, and if it's hot enough, it doesn't trigger the electric coil to heat at all. You have that redundant system though, because as I mentioned, this only works when it's running, and so if it's spring or fall and you're not running your air conditioning and heating, you won't have domestic hot water production. So it's a bit of belt and suspenders, but it can dramatically reduce your hot water cost generation. The split system, this box here is the box that is connected to the ground loop. Usually it sits in your basement. I use a refrigerant line set just like I would on a traditional air conditioning set to connect this box to another box inside. That could be an air handler unit like this. It can be a furnace, a coil on top of a furnace setup like this. It can be a fan coil unit. It could be a space pack unit or a Unico unit, high velocity system unit. Those work as well. Again, these have the ability to create domestic hot water. The VRF system, variable refrigerant flow system, sometimes called variable refrigerant volume systems, depending on the manufacturer. The difference between this and the slide before is that this box, again, sits inside, and then it can connect to multiple boxes inside. So I can have one box connected to the ground loop, and I can share that capacity with other, air handling units, fan coil units, ducted fan coil units, unducted or ductless units that might sit there or be recessed into a ceiling. You can go into some manufacturers have a furnace coil that it can connect to, so you can blend it in with an existing system. So again, it really depends on the manufacturer, and not all manufacturers have a water-cooled single phase version of this. You need single phase electric because that's what residential buildings have. They make these in 3-phase, but the single phase is what we need. So there's a couple of manufacturers that have them. I think more are coming on. 5 years ago you couldn't already get them, but now there's other ones that are having them. So that's it makes it a very versatile installation type. And then the water system, again, this box is connected to the ground loop, and it produces chill water at 40 to 45 degrees, and it produces hot water up to 120 degrees. And then you can circulate that through piping to water coils that are mounted in air handling units, furnaces, Unico space pack. You can use heating only applications for radiant floor. Again, you can make domestic hot water directly out of this machine or through an indirect water heater if you wanted a larger volume. And so they're very flexible. They cost, they're probably of the Geo choices. This is probably one of the more expensive ones, and it's also one of the least efficient ones. So there are places that's really the only way you can go, which is why we use them. But if you have a choice, this isn't the most efficient method. Here's an example of a house that's got 3 different systems. It's got a self-contained system, probably serving the basement and first floor. It's got a split system that this is probably connected to an air handling unit, maybe in the attic to service the second floor. Then I got a water-to-water unit that's producing hot water, maybe for domestic or for floor heat. Air source heat pumps. I've got the big thing with the air source heat pump is it's almost always going to be lower first cost. It'll, the Geo will pay for itself over time, but it might take a while. So, but when you compare it to geothermal, it's less efficient, higher CO2 emissions, operating costs, site energy use, maintenance costs. Again, I've got a box sitting outside and a box inside, so inherently I just have 2 machines to repair them or keep them running than one. Shorter average equipment life, and that's just again because the exterior unit is going to age faster. And then with all heat pumps, we have a reduced capacity as air temperatures drop or go up. I mean, it works in both directions, but we're most concerned about it in the heating season. And air source heat pumps have gotten a lot better about having good capacity when we get into the winter months down to real low temperatures. But there is a degradation of capacity. You need to make sure you get one that will give you everything you need at the lowest temperature you expect to have. And because when you're not using a heat pump, it switches over to electric resistance, which is the most expensive way to heat your house. So you want to just be aware that that's a situation. And here's some examples of some of that equipment. There's a one-to-one situation with a mini split. Here's a situation where I'm making hot water. I'm connected to my air handling unit that's producing forced air. Here's a water-to-water installation where I've got an outdoor box and indoor box, and then I'm making hot water for domestic use, and I'm making floor radiant and radiators. Then the last one is this, I believe, a Daikin system, and it's just showing you the various things you can do with these systems. You know, here's a furnace A coil, so I've got a gas-fired unit with a cooling coil stacked on top that hooks to this, and I'm also hooked to a couple of other fan coil style units that deliver cooling directly. Here I've got 2 furnaces. Here I've got one-to-one furnace. Here I've got some air conditioning stuff. So it's just a really flexible system to install. It's very efficient. And as long as you make sure that you're covered for extreme low temperatures primarily, they're a very effective and lower cost alternative to geo. And a lot of these high efficiency systems have tax credits currently with the federal government, and some rebates also that help reduce the overall cost. And that's all I got.
Thank you so much, Mark. I have just a couple quick questions. How big of a field do you generally need for a ground system? It depends on the size of the building, I'm sure, right?
Correct. And I'm looking to try and find get me back up here so I can see you guys. Well, regardless, yeah, it completely depends on how much energy or how much capacity you need in the field. So it could be a rule of thumb, which we really don't like to use in geothermal, but we do still, is that 150 to 200 linear feet of borehole per ton. Again, it's a little tricky. You got to make sure that you don't undersize or oversize. It's always best to have a professional or a qualified contractor install it. But that's a loose number, 150 to 200. So a 500-foot hole will be somewhere around 3 tons.
Yeah. Okay.
That ballpark.
Yeah. Okay. Thank you. What percentage of your clients install radiant floor heating, if so, or in limited areas like bathroom?
A lot of people like radiant floor systems, and Geo is perfect for a radiant floor system. It's got the temperature profile is really good, so there's often that piece. With any radiant floor though, if you want an air conditioning system and you want radiant floor, wherever you're doubling that up, you're adding cost to the project, and that's true of conventional systems or Geo systems. The nice thing, and with Geo, they do have some equipment that will produce, conditioned air that will also will produce a little hot water for a radiant floor. So there's some flexibility there. And I forgot to mention in the talk that high temp heat pump can be used. Radiant or Geo hot water doesn't heat up quite enough for a standard cast iron system. It wants a little hotter air or a lot hotter water. So that high temp unit will get up to 160 degrees. So you can use it in a cast iron system and get real good performance.
Okay. Great, Mark. Thank you so much. Very informative and very exciting.
Well, good.